Welcome to the Microbe Explorer. Let's read today the two-kingdom gram-positive and gram-negative bacteria through microscope.
Under a clinical microscope, bacteria immediately divide into two visual baseline categories: gram-positive cells that stain a deep purple and gram-negative cells that stain pink. But as we penetrate the cellular envelope, the reason for this contrast becomes clear. The gram stain operates as a direct readout of nanostructural reality. The color a bacterium displays is an exact reflection of how it is physically built. This cellular dichotomy comes down to two opposing architectural strategies: constructing a massive, thick layer of peptidoglycan, or deploying a thinner wall protected by a lipid-rich outer membrane. This structural divergence at the cell envelope dictates every downstream clinical vulnerability. It controls how the human immune system mounts its defense, and it directly determines which pharmacological weapons will successfully destroy the pathogen. This diagram illustrates both cellular models, starting from their shared baseline, the inner lipid bilayer. On the gram-positive side, the cell builds a highly dense, multi-layered peptidoglycan matrix, reaching 20 to 80 nanometers thick. Because of this extreme thickness, the gram-positive wall is rigid and provides virtually no elasticity under physical stress. The gram-negative side relies on a single-layered peptidoglycan matrix. At 8 to 10 nanometers thick, it offers less rigidity, but significantly higher elasticity. We can now see the mechanical origin of the visual phenotype. During alcohol decolorization in the laboratory, the thick peptidoglycan dehydrates, trapping large crystal violet dye complexes inside. The thin layer cannot hold the molecules, allowing the dye to flush completely out. Maintaining this massive structural barrier requires immense energy. Gram-positive bacteria operate with a staggering 8-to-1 RNA to DNA ratio to support continuous wall synthesis, whereas gram-negative bacteria manage a highly efficient 1-to-1 ratio. The primary defense mechanism of a gram-positive cell is simply sheer physical mass. That density dictates its high metabolic cost, its mechanical rigidity, and its defining purple laboratory readout. Returning to our diagram, we see transmembrane structures unique to each build. To keep the massive gram-positive matrix intact, long chains of teichoic acids weave vertically through the wall, anchoring the layers together. Beneath this matrix, the gram-positive plasma membrane features prominent mesosomes, deep structural invaginations folding inward to increase the surface area of the cell interior. Shifting to the gram-negative architecture, an entirely different envelope develops. Directly above the thin peptidoglycan sits a defined fluid-filled gap known as the periplasmic space. Above this space lies the defining evolutionary feature of gram-negative bacteria, a lipid-rich outer membrane capping the cell. Because this outer membrane seals the cell from the environment, specialized access gates are required. Porins, highly selective protein channels, are embedded directly into this top layer to filter molecular transport. The double membrane dictates how appendages are built. To anchor a flagellum, the gram-negative basal body requires 4 rings to securely penetrate its complex envelope, while the gram-positive architecture only requires 2. Gram-negative bacteria sacrifice the raw thickness of peptidoglycan to build a highly sophisticated dual-membrane fortress with restricted entry points. The chemical makeup of these envelopes dictates their toxicity. The gram-positive wall exhibits very low overall lipid content, and its structural proteins rely on only a few varieties of amino acids. By contrast, the gram-negative envelope is incredibly lipid-rich. The presence of the outer membrane introduces several distinct aromatic and sulfur-containing amino acids into the structural profile. This diagram highlights the most consequential component of that profile. Highly complex lipopolysaccharides, or LPS, are integrated into the gram-negative outer membrane, protruding outwardly in dense formations. LPS chains function as endotoxins. This means their extreme toxicity is permanently bound directly to the bacterium's physical structure. It is not an external product. It is the wall itself. Gram-positive pathogens utilize exotoxins instead. These are entirely separate proteins that the cell actively synthesizes and secretes away from its body to attack the host environment. Because a gram-negative bacterium is constructed from structural endotoxins, its physical presence inherently triggers severe physiological reactions, forcing the human immune system to engage it differently than an actively secreting cell. When subjected to physical disruption or severe desiccation, the sheer density of the gram-positive wall ensures a high rate of survival, while the thin, elastic gram-negative envelope fractures under the same physical stress. Biological weapons apply a different pressure. The enzyme lysozyme specifically cleaves the bonds within a peptidoglycan matrix, rapidly deteriorating the gram-positive defense. Yet against gram-negative bacteria, lysozyme fails. The lipid outer membrane acts as an absolute blockade, repelling the enzyme long before it can reach the vulnerable layer below. Penicillin attacks the same vulnerability, actively halting peptidoglycan synthesis. Without the ability to maintain its massive wall, a gram-positive bacterium quickly dies. The efficacy of this mechanism was so clear that pharmaceutical companies constructed massive assembly lines explicitly dedicated to mass-producing penicillin to exploit this structural weakness. Pure crystalline penicillin was heavily regulated as an investigational drug, deployed with clinical precision specifically to defeat thick-walled pathogens. However, because the gram-negative architecture features an outer lipid membrane that repels basic dyes and large molecules, these pathogens exhibit an inherently low susceptibility to penicillin. To bypass the outer membrane, researchers isolated an inverse set of pharmacological weapons. Antibiotics like streptomycin, chloramphenicol, and tetracycline are highly effective specifically because they can penetrate the complex gram-negative architecture. Antibiotic selection relies entirely on a mechanical calculation. The physician is choosing a molecular tool designed specifically to defeat either a massive peptidoglycan wall or a restrictive lipid outer membrane. These cellular models map securely onto the taxonomy of real-world pathogens, defining their shape and behavior. Gram-positive bacteria predominantly display as round cocci or rod shapes that are capable of forming protective spores. This structural group encompasses major pathogenic families, including Staphylococcus, Streptococcus, Bacillus, and Clostridium. Their clinical hallmarks track exactly with their architecture. They rely on thick walls, secrete potent exotoxins, and possess the unique ability to produce dormant endospores during periods of unfavorable environmental stress. Gram-negative bacteria, by contrast, predominantly present as non-spore-forming rods or coccobacilli. This envelope classification includes dangerous families like Escherichia, Salmonella, Pseudomonas, and Helicobacter. Their resulting clinical behavior is defined by the restrictions of their outer membrane, the transport control of their embedded porins, and the highly reactive LPS endotoxins permanently locked into their structure. The gram stain divides bacteria by color in a matter of minutes. But that clinical contrast reveals the precise architectural schematic required to predict a pathogen's behavior and to select the exact antimicrobial force needed to dismantle it.
Thanks for watching the Microbes Explorer. If you liked the video, please like, share the video, and subscribe the channel for more interesting videos.